Consider the solids in Figure 9.25 in which congruent circles lie in parallel planes. For the circles on the left, suppose that centers O and O' are joined to form segment OO'. Similarly, suppose that segment QQ' joins the center of the circles on the right. Line segments such as segment XX' join 2 points of the circles on the left, so that segment XX' is parallel to segment OO'. If all such segments, like segments XX', YY', and ZZ', are parallel to each other, then a cylinder is generated. Because segment OO' is not perpendicular to planes P and P', the solid on the left is an oblique circular cylinder. With segment QQ' perpendicular to planes P and P', the solid on the right is a right circular cylinder. For both cylinders, the distance h between the planes P and P' is the length of the altitude of the cylinder. H is also called the height of the cylinder. The congruent circles are known as the bases of each cylinder. A right circular cylinder is shown in Figure 9.26. However, the parallel planes are not pictured. The line segment joining the centers of the two circular bases is known as the axis of the cylinder. For a right circular cylinder, it is necessary that the axis be perpendicular to the planes of the circular bases. In such a case, the length of the altitude h is the length of the axis. The formula for the lateral area of a right circular cylinder, found in the following theorem, should be compared to the formula L equals H P, the lateral area of a right prism whose base has perimeter P. Theorem 9.3.1. The lateral area L of a right circular cylinder with altitude of length h and circumference C of the base is given by L equals H C. Alternative form. The lateral area of the right circular cylinder can be expressed in the form L equals 2 pi RH, where R is the length of the radius of the circular base. Theorem 9.3.2. The total area T of a right circular cylinder with base area B and lateral area L is given by T equals L plus 2 B. Alternative form, where R is the length of the radius of the base and H is the length of the altitude of the cylinder, the total area can be expressed in the form T equals 2 pi RH plus 2 pi R squared. For the right circular cylinder shown in Figure 9.27, find the A. Exact lateral area L, B. Exact surface area T. Solution. Alternative form, where R is the length of the radius of the base and H is the length of the altitude of the cylinder, the total area can be expressed in the form T equals 2 pi RH plus 2 pi R squared equals 2 pi times 5 times 12. L equals 120 pi inches squared. B. T equals L plus 2 B equals 2 pi RH plus 2 pi R squared equals 2 times pi times 5 times 12 plus 2 times pi times 5 squared equals 120 pi plus 50 pi. T equals 170 pi inches squared. In considering the volume of a right circular cylinder, recall that the volume of a prism is given by V equals BH, where B is the area of the base. In Figure 9.28, we inscribe a prism in the cylinder as shown. Suppose that the prism is regular and that the number of sides in the inscribed polygon's base becomes larger and larger. Thus, the base approaches a circle in this limiting process. The area of the polygonal base also approaches the area of the circle, and the volume of the prism approaches that of the right circular cylinder. Our conclusion is stated without proof in the following theorem. Theorem 9.3.3. The volume, capital V, of a right circular cylinder with base area, capital B, and altitude of length h is given by capital V equals capital B h. Alternative form, where r is the length of the radius of the base, the volume for the right circular cylinder can be written capital V equals pi r squared h. If d equals 4 centimeters and h equals 3.5 centimeters, use a calculator to find the approximate volume of the right circular cylinder shown in figure 9.29. Give the answer correct to 2 decimal places. Solution: d equals 4, so r equals 2. Thus, capital V equals capital B h, or capital V equals pi r squared h becomes capital V equals pi times 2 squared times 3.5. This equals pi times 4 times 3.5. Volume equals 14 pi centimeters cubed. Volume is approximately equal to 43.98 centimeters cubed. Table 9.2 should help us recall and compare the area and volume formulas. Table 9.2. Prism. Lateral area is capital L equals H times capital P. Total area, capital T equals capital L plus 2 capital B. Volume, capital V equals capital B H. Cylinder. Lateral area is capital L equals H times capital C. Total area, capital T equals capital L plus 2 capital B. Volume, capital V equals capital B times H. In figure 9.30, consider point P, which lies outside the plane containing circle O. A surface known as a cone results when the line segments are drawn from point P to points on the circle. However, if point P is joined to all possible points on the circle, as well as to points in the interior of the circle, a solid is formed. If segment PO is not perpendicular to the plane of circle O in figure 9.30, the cone is an oblique circular cone. In figures 9.30 and 9.31, point P is the vertex of the cone, and circle O is the base. The segment PO, which joins the vertex to the center of the circular base, is the axis of the cone. If the axis is perpendicular to the plane containing the base, as in figure 9.31, the cone is a right circular cone. In any cone, the perpendicular segment from the vertex to the plane of the base is the altitude of the cone. In a right circular cone, the length h of the altitude equals the length of the axis. For a right circular cone, and only for this type of cone, any line segment that joins the vertex to a point on the circle is a slant height of the cone. We will denote the length of the slant height as script L as shown in figure 9.31. Recall now that the lateral area for a regular pyramid is given by capital L equals 1/2 L times capital P. For a right circular cone, consider an inscribed regular pyramid as in figure 9.32. As the number of sides of the inscribed polygon's base grows larger, the perimeter of the inscribed polygon approaches the circumference of the circle as a limit. In addition, the slant height of the congruent triangular faces approaches that of the slant height of the cone. Thus, the lateral area of the right circular cone can be compared to capital L equals 1/2 L times capital P. For the cone, we have capital L equals 1/2 L times capital C, in which capital C is the circumference of the base. The fact that capital C equals 2 pi r leads to capital L equals 1/2 L times 2 pi r. So, capital L equals pi r L. Theorem 9.3.4. The lateral area, capital L, of a right circular cone with slant height of length script L and circumference capital C of the base is given by capital L equals 1/2 L times capital C. Alternative form, where r is the length of the radius of the base, capital L equals pi r L. The following theorem follows easily from Theorem 9.3.4. Theorem 9.3.5. The total area, capital T, of a right circular cone with base area, capital B, and lateral area, capital L, is given by capital T equals capital B plus L. Alternative form, where r is the length of the radius of the base, and script L is the length of the slant height, capital T equals pi r squared plus pi r L. For the right circular cone, in which r equals 3 centimeters and h equals 6 centimeters, see figure 9.33, find the A. Exact and approximate lateral area, capital L. Solution. We need the length of the slant height, script L, for each problem part, so we apply the Pythagorean theorem. L squared equals r squared plus h squared equals 3 squared plus 6 squared equals 9 plus 36. L squared equals 45. L equals the square root of 45, which equals the square root of the product 9 times 5. Slant height L equals 3 square root of 5. Using capital L equals pi r script L, we have capital L equals pi times 3 centimeters times 3 square roots of 5 centimeters. Capital L equals 9 pi square root of 5 centimeters squared. Capital L is approximately 63.22 centimeters squared. For the right circular cone, in which r equals 3 centimeters and h equals 6 centimeters, see figure 9.33, find the B. Exact and approximate total area, capital T. Solution. Capital T equals capital B plus capital L, equal to pi r squared plus pi r L, with L equal 3 square root of 5 from part A, equals pi times 3 squared plus pi times 3 square root of 5. Capital T equals the quantity 9 pi plus 9 pi square root of 5 centimeters squared. Capital T is approximately equal to 91.50 centimeters squared. The following theorem was demonstrated in the solution of example 4. Theorem 9.3.6. In a right circular cone, the lengths of the radius r of the base, the altitude h, and the slant height script L satisfy the Pythagorean theorem. That is, L squared equals r squared plus h squared in every right circular cone. Recall that the volume of a pyramid is given by the formula capital V equals 1/3 capital BH. Consider a regular pyramid inscribed in a right circular cone. If its number of sides increases indefinitely, the volume of the pyramid approaches that of the right circular cone. See figure 9.34. Then the volume of the right circular cone is capital V equals 1/3 capital BH. Because the area of the base of the cone is capital B equals pi r squared, an alternative formula for the volume of the cone is capital V equals 1/3 pi r squared h. We state this result as a theorem. Theorem 9.3.7. The volume capital V of a right circular cone with base area capital B and altitude of length h is given by capital V equals 1/3 capital BH. Alternative form. Where r is the length of the radius of the base, the formula for the volume of the cone is usually written capital V equals 1/3 pi r squared h. Table 9.3 should help us to recall and compare the area and volume formulas. Table 9.3, pyramid, lateral area, capital L equals 1/2 L capital P. Total area, capital T equals capital B plus capital L. Volume, capital V equals 1/3 capital BH. Slant height, L squared equals A squared plus H squared. Cone, lateral area, capital L equals 1/2 L times capital C. Total area, capital T equals capital B plus capital L. Volume, capital V equals 1/3 capital BH. Slant height, L squared equals R squared plus H squared. Suppose that part of the boundary for a plane region is a line segment. When the plane region is revolved about this line segment, the locus of points generated in space is called a solid of revolution. The complete 360-degree rotation moves the region about the edge until the region returns to its original position. The side, edge, used is called the axis of the resulting solid of revolution. Describe the solid of revolution that results when a rectangular region with dimensions 2 foot by 5 foot is revolved about the 5 foot side, see figure 9.35a. b. A semicircular region with radius of length 3 centimeters is revolved about the diameter shown in figure 9.35b. a. In figure 9.35a, the rectangle on the left is revolved about the 5 foot side to form the solid on the right. The solid of revolution generated is a right circular cylinder that has a base radius of 2 feet and an altitude of 5 feet. b. In figure 9.35b, the semicircle on the left is revolved about its diameter to form the solid on the right. The solid of revolution generated is a sphere with a radius of length 3 centimeters. It may come as a surprise that the formulas that are used to calculate the volumes of an oblique circular cylinder and a right circular cylinder are identical. To see why the formula V equals BH or V equals pi r squared h can be used to calculate the volume of an oblique circular cylinder, consider the stacks of pancakes shown in figure 9.37a and 9.37b. With each stack h units high, the volume is the same regardless of whether the stack is vertical or oblique, since both the height of the stack and the area of each base are congruent. It is also true that the formula for the volume of an oblique circular cone is V equals 1/3 BH or V equals 1/3 pi r squared h.